All right, welcome back. In this module, we're moving from sort of the earlier summaries and the overview of some of the statistical tools that we'll use into correlation and regression. So these come from chapters 4 and 11 in Naked Statistics. And together they explain how we find and quantify relationships in data. So everything from why Netflix knows what movies you like to why some jobs are more dangerous to your health than others, even when no one's swinging a hammer. We'll start with correlation, what it measures and its limits. Then we'll build up to regression analysis, which allows us to go a step further. It's actually isolating the effect of one variable while holding others constant. And that's really important to be able to do that. By the end of the chapter, the end of the module, you'll understand the core logic behind a huge share of real-world statistical research. So correlation measures the degree to which two variables are related. When Netflix recommends a documentary about Benazir Bhutto because you loved Fog of War and Enron, the smartest guys in the room, it isn't because some analyst studied your life story, went through and detailed all of your likes and dislikes. It's because your ratings correlate with other viewers who also love those films, and their favorites become your recommendations. Two variables are positively correlated when they move in the same direction. Taller people tend to weigh more. They're negatively correlated when they move in the opposite direction. People who exercise more tend to weigh less. Correlation doesn't require every single observation to fit the pattern, and oftentimes when you look at data, you can point out to yourself, hey, I know, something that doesn't fit that correlation, doesn't fit that pattern. Some short people out there outweigh tall people. But what matters is the overall tendency across a large group. That relationship gets captured in one number, the correlation coefficient, also called lowercase r. It always falls between -1 and +1. So a correlation of 1 means a perfect positive relationship. Every change in one variable comes with a matching change in the other variable. -1 is a perfect negative relationship. And a correlation near 0, like shoe size and SAT scores, tell us that there's no meaningful association at all. What makes R so powerful is that it has no units. It works whether you're comparing inches and pounds or the number of televisions in a home and SAT scores. For real-world context, the correlation between height and weight for American men is only about 0.4. So a real relationship, a positive relationship, but far from perfect. So there are a lot of observations that don't fit that pattern. Here's the catch that runs through the whole chapter. Correlation does not imply causation, and you might have heard that already. There's a real correlation between how many TVs a family owns and their children's SAT scores. But that doesn't mean that simply buying extra televisions is going to boost your child's test performance. The likely explanation here and what's causing this correlation is the third variable. In this case, probably parental education and income that drives both the number of televisions in the home and the SAT scores. Families with more resources tend to own more electronics and also tend to have children who score better on standardized tests. And the data bears this out directly. Students from families earning over $200,000 a year average 586 on the SAT math section, compared to 460 for students from families earning $20,000 or less. Whenever you see a correlation, the next question should always be, what else might explain this? That question, what else might explain this, is exactly what regression analysis is built to answer. So chapter 11 in Naked Statistics opens with a striking finding from the Whitehall studies of British civil servants. It's not the high-pressure executives who face the greatest risk for heart disease. It's workers with low control over their day-to-day tasks. But the issue is we can't randomly assign thousands of people to different jobs for years and see who develops heart disease. That's not ethical, and it's also not practical. Instead, researchers need a tool that could take observational data, so the messy real-world kind where it's not set up perfectly like an experiment, and isolate the effect of job control from everything else that differs between low status and high status workers. So things like smoking, their income, their access to healthcare, even their education level. The tool that can do that is regression analysis. At its core, Regression finds the straight line that fits a scatter of data points. This technique is called ordinary least squares, or OLS. Every point, every single point on that scatter plot has a residual from the line of best fit. So that's the vertical distance between the actual observation and the line. What the OLS does is it chooses the line that minimizes the sum of the squared residuals, which gives extra weights to the point that are pretty far from the line. The result is a regression equation, so y equals a plus b times x. Using height and weight from the changing lives studied, the equation comes out to weight equals negative 135 plus 4.5 times the height in inches. We call that 4.5 the regression coefficient. The regression coefficient, that 4.5, tells us that each additional inch of height is associated with 4.5 additional pounds on average. For any coefficient, three questions matter: the sign, the size, and the significance. The sign tells us the direction. Is the relationship positive or negative? This is very important in and of itself. Size tells us whether the effect is large enough to matter in the real world. And significance tells us whether the result is likely a real pattern or just sampling noise. We test significance the same way we test other estimates, using a standard error and a confidence interval. If the confidence interval for a coefficient doesn't include 0, we reject the null hypothesis that there's no relationship. But you have to be careful. Statistical significance doesn't always mean practically important. So the book gives a memorable example. Whiter teeth might be associated with $86 more in annual income, and that result could be statistically significant with a huge sample. But $86 a year is not exactly life-changing. And this is where regression becomes really powerful. We can add multiple explanatory variables. So things like age, sex, education, exercise, poverty status, race, all of these things into a single equation so that we're able to account for all these differences for each observation. Each of the coefficients related to each of those variables that we include estimates the effect of that one variable while holding all the other variables constant. The book offers a helpful mental picture. So imagine sorting every person into rooms where everyone shares the same height, the same age, the same sex, the same income. Within each room, the only thing left varying is education. So whether the relationship remains between education and weight in every room combined is the coefficient regression gives us. As we add more explanatory variables, R squared, the share of the total variation explained by the model climbs. In this case, it goes from 0.25 to 0.29. That still leaves plenty of unexplained variation, which is completely normal in social science data. But as we add more variables, what we tend to see is the R squared increases because we're able to account for more of the differences between the observations. So to bring it all together, correlation tells us that two things move together. Regression lets us dig deeper and ask what happens to that relationship once we control for everything else that we can measure. That's how researchers concluded that low job control predicts heart disease independent of smoking and income, and how economists showed that most, though not all, of the gender pay gap among MBA graduates can be explained by differences in coursework, in career interruptions, and in hours worked. Regression is an incredibly powerful tool, but as we'll see in the next chapter, it's also easy to misuse.